Hello and welcome to Unit 3 of Lesson 1. In this unit, we introduce the concept of modeling. Specifically, we introduce the concept of modeling of causal links between the elements in a system. In order to help us develop and communicate our understanding of the complex cause and effects relationships between ourselves and the ocean, we need to develop models which map these relationships. One such modeling framework is the DAPSIWR framework, which we introduce in this unit. So, the objectives of this unit are, first of all, we introduce the concept of systems thinking as a means of putting the responsible approach to modeling into context. Then we will describe the DAPSIWR framework. This is the framework used to describe the chain of causal links involved in the interaction between human, for example, economic, and natural systems, for example, ecosystems. Then we will introduce the responsible knowledge base, a means of using the DAPSIWR framework to model human-ocean interactions, backed up by scientific and other evidence. And then we will demonstrate how the knowledge base is used to create DAPSIWR models, using examples from the responsible work on documenting important stories of human-ocean interaction. After studying the materials in this unit, you will be able to explain the concept of systems thinking and how it can be used to develop a deeper understanding of the world around us. Use the DAPSIWR framework to create models of interactions between human and natural environments. Know how the knowledge base is used to create models using the DAPSIWR framework. And then use the background reading materials or links to it provided to deepen their knowledge of the topics introduced in this unit. So, what are we talking about when we speak about seeing the big pictures? The old Indian stories of the blind man and the elephant is often used to illustrate a number of different phenomena. They each touch a different part of the elephant and have a very different opinion on what it is. The story is used to illustrate things such as the nature and limitation of subjective experience, the importance of communication, respect for different perspectives, and the importance of getting a complete picture before drawing conclusions or taking action. We easily fall into the trap of trying to understand systems by breaking it down into individual component parts and studying each of those separately. But as Donella Meadows said, the behavior of a system cannot be known just by knowing the elements of which the system is made. So, what is a system? There are many different definitions of system, and they seem quite different. But in fact, they have a lot in common. Systems are defined not just by the individual parts or components, but by their connections or relationships and how these parts interact with each other. Systems can be closed. By this, we mean that they interact very little or not at all with other external systems. For example, a closed-circuit TV system is designed to be isolated from interference or transmission to or from cameras or monitors outside the systems, making it more secure. Open systems, on the other hand, are open to exchange with the outside world. For example, a thermos vacuum flask is often used as an example of a closed system, as it doesn't allow heat exchange with the outside environment. However, if you take the lid off the flask, it immediately becomes an open system, interacting with the air around it. So, what is a system really? Clearly then, a system must be composed of elements which interact. This interaction goes to defining the behavior of the system. While individual elements of the system may have behaviors of their own, when these are combined with the behaviors of other elements and their interactions, the behavior of the system can become very complex indeed. The system may have a function or a purpose, although this is hard to define for larger systems than small ones. Man-made systems tend to have a specific purpose, whereas natural systems have evolved to work in a particular way which may seem purposeful to us as observers. The human body is incredibly complex. Estimates vary, but are trillions of cells in the human body, with a huge variety of cell types, each performing their complex functions and interacting with the other cells in the body. Each cell is a complex system in its own right, but to understand how a football team functions, it is probably not necessary to model the system right down to individual cells. So, is this too much information? Yes, if we try to understand complex systems right down to the lowest level, we lose the big picture. It is very difficult to see both the big picture and the smallest level of detail at the same time. That is why, when we study systems, we must decide the level of abstraction at which we can comfortably work, and which aids our understanding of the system and how it behaves. For example, when studying forest, it is better not to model down to individual cell level. If we want to understand trees, for example, we can study the tree, but to understand the forest as a system, we must understand how the various elements of that forest system interact with each other. System thinking is the development of understanding how the individual elements interact with each other, thereby influencing each other and determining the behavior of the system as a whole. So we need mental models of things in order to understand them and discuss them with others. Effectively, we create representations of reality which help us to understand them and how they behave. We can go further and use our models to simulate various scenarios or situations to see how the system might behave. If our model is good and accurate, it will give us useful insights. A mental model is a kind of internal symbol or representation of external reality. So, mental models are simply our own explanation or understanding of a real life system or situation. Our minds are powerful enough to build internal models of situations which we can improve through experience and observation. Using these mental models, we are able to simulate different scenarios and possible outcomes. So, how do we share our understanding? Going back to the blind man and the elephant, their individual mental models were initially restricted and unable to explain the entire elephant. But by gathering more data and sharing it with each other, they could have created a more comprehensive picture of the elephant. This would have been more useful and a better representation of the reality. Clearly, if our models does not fit with observed reality, then it is either incorrect or incomplete or both. But when dealing with real-life systems, we normally must observe the system over a certain period of time to know whether our model is correct or not. This approach of seeing systems not just as a collection of independent parts, but as a dynamic system of interconnected elements is called systems thinking. By using the tools and techniques of systems thinking, we can create better understanding of systems and how they behave. What is systems thinking? Well, we could start by asking the opposite question. What is not system thinking? An example of these would be linear thinking, where, for example, we treat individual symptoms rather than understanding and treating underlying causes, or where we try to optimize the performance of individual parts of a system without optimizing the performance of the system as a whole. This kind of thinking inevitably leads to some undesirable side effects. Clearly, when we are dealing with complex situations, we need to consider the consequences of our actions. While promoting tourism will probably increase local wealth in the short term, the long term consequences can be quite undesirable. Increased pressure on the environment due to waste and increased use of water resources can have knock on effects on existing industries and ultimately damage what made the area so attractive in the first place. Fixing problems cannot be done by using simple linear thinking. Sustainable solutions can only be found through application of systems thinking. Systems thinking is a way of helping us to see the big picture. It can help us to resolve complex situations involving people and things, looking at the interconnections between parts of the whole rather than just concentrating on the parts. Some people refer to it as joined up thinking. It is important because it gives us tools for dealing with complexity and gaining deeper understanding of complex issues. This helps us to eliminate personal opinion and biases and focus on the evidence, building that big picture we need to see more clearly. There are many excellent resources available to help us become better systems thinkers. Unfortunately, there is not a single universal definition of what a systems thinker is, but they are characterized by their interest in understanding systems. This kind of understanding helps us to figure out ways to improve systems based on a solid understanding of the underlying system model and by gathering and analyzing information to back up our decisions. At the end of this presentation, you will find some useful resources which will help you become a better systems thinker. The habits of a system thinker, developed by the Waters Foundation, encompass a spectrum of thinking strategies that foster problem solving and encourage questioning. Though habit is defined as a usual way of doing things, the habits of a system thinker do not suggest that systems thinkers are limited by routine ways of thinking. Rather, the habits encourage flexible thinking and appreciation of new, emerging insights and multiple perspectives. There are a number of tools which are widely used in creating diagrams to draw mental models or systems. The most common type of systems diagram is the causal loop diagram. There is a huge amount of online resources available for those interested in gaining a deeper knowledge of using causal loop diagrams to model systems. You will find a short list at the end of this presentation. In causal diagrams, we show the direction of cause and effects relationships using an arrow. A plus sign or letter S at the arrow end means that there is a positive relationship between cause and effect. The two variables change in the same direction. For example, an increase in births causes an increase in population. A minus sign at the arrow end means that there is a negative relationship between cause and effect. Likewise, the letter O tells us that the two variables change in the opposite direction. In this case, an increase in births causes an increase in population. We can make our model more detailed by combining those relationships which we know about. So in our example, the overall population is affected by both the rate of births and the rate of deaths. In this example, we add two more loops with the double symbols on them to indicate there is a delay relationships between the two variables. As the population increases, after some time this will lead to further births. Likewise, it will in time lead to deaths as people get older. Finally, we could take into account other parameters. For example, as the population grows, the available resources such as material resources and mutual support increase. This will lead to better living conditions and therefore increased life expectancy. Living longer could lead to a decrease in family size. There might also be a relationship between desired family size and number of births per person. Loops in the diagram may be labeled as R for reinforcing loops, which create positive feedback. In this case, population would increase uncontrollably unless there was a balancing B loop or negative feedback loop whereby deaths and births keep the population in balance. The additional loops increase the complexity of the model and will cause some interesting effects over time. DAPSIWR is a causal framework for describing the interactions between society and the environment. DAPSIWR is used to describe a chain of causal links and is thus useful in describing the relationship between the origins, consequences, and responses of environmental problems. There are many variations on the original DAPSIWR framework, which was adopted by the European Environmental Agency. In the DAPSIWR project, we have adapted and modified this framework to support the modeling of the human-ocean relationship in a more complete fashion. This adapted form of the DAPSIWR framework is DAPSIWR, standing for drivers, activities, pressures, states, impacts, welfare, and responses. Drivers require a set of activities to these changes needs. These activities may cause multiple pressures, which may lead to state changes in the natural system. State changes may result in impacts on the environment and ultimately on human welfare. That will need to be addressed through responses. Responses can take either part of the DAPSIWR approach, from modifying drivers to technological development, focused, for example, on minimizing impacts. Drivers are effectively the needs which drive human activity. Examples of primary drivers are the need for food and shelter. Examples of secondary drivers are the need for entertainment and culture. Activities are the human activities which we carry out to fulfill our needs and which lead pressures on the environment. An example of activity is fishing in response to the driver of the need for food. Pressure on the environment happens as a result of human activities. Pressures can be divided into different types. For example, use and depletion of natural resources, changes in land use, or emissions into the environment such as waste, radiation, or noise. As a result of pressures, the state of the environment is affected. The quality of the components of the environment, such as air, water, soil, can be degraded. Where changes in state occur, this can have impacts on the quality and functioning of environment and ecosystems, and their ability to function. Ultimately, environmental impacts can have impacts on human health and welfare also. Society, either directly or through policy, can respond to the impacts by targeting the earlier part of the chain. For example, by encouraging people to adopt different means of transport. We can target specific drivers, which in turn will limit activities such as the use of private car, thereby reducing emissions. In the DAPSIWR project, we are developing our own modeling tool, which allows us to create DAPSIWR models for specific stories. Each story represents a specific issue of concern, such as, for example, coastal tourism or microplastic in the ocean. By using the DAPSIWR framework and our tool, we can create our own causal maps, or what the chain of cause and effect relationships, to help us understand and explain each story. Different icons are used to represent drivers, pressures, activities, etc. In this picture, we see a highly simplified version of the DAPSIWR, just to illustrate the use of the modeling tool to capture the causal relationships between drivers, pressures, and so on. You will also notice that we can link evidence to each link in the chain. For example, if we have a scientific article relating to coastal debris caused by tourism, then we can create a link to this article in the modeling tool. Similarly, when we have evidence documenting the relationship between, for example, a state of change and an impact, we can also link this evidence to the relationship. In the above example, we may have a documentary film which explains how the change in ocean state caused by chemicals leaching from plastic debris causes injury to life in the ocean. We can also link actors to specific activities. In this way, we can keep track of which stakeholders are involved at which points in the DAPSIWR. All of the stories and related evidence are stored in a knowledge base linked to the modeling tool. It is our intention to make this tool and knowledge base available as a public resource to help us build and share better models and evidence relating to topics of importance in relation to ocean literacy. It will allow marine scientists, ocean literacy experts, domain experts in general to create rich integrated models representing the human-ocean relationship, ocean economy and related knowledge on ocean literacy. It will facilitate searching for available knowledge and on the human-ocean relationships that can help developing ocean literacy products. Attached to this unit, you will find this presentation. At the end of the presentation, you will find links to useful resources on systems thinking and on causal diagrams. Thanks for listening.